Right now, somewhere out in the world, a paralyzed patient is staring at a screen, and they're completely motionless, yet they're somehow typing out a text message at 22 words per minute.
Wow.
Yeah. Meanwhile, in a research lab, scientists are filling a syringe with this cloudy liquid. And when they inject that liquid into a patient's belly fat, it doesn't just, absorb into the body. It actually magically snaps together to form a fully functioning miniature liver.
Which is just wild to think about.
It really is. Welcome to the deep dive.
It's a profound shift we're seeing. And for you listening right now, we are basically going to act as your guides through what is an absolute avalanche of recent scientific breakthroughs.
Seriously, we have a massive stack of sources on the table today. We're pulling from the latest ACM tech news, a towering stack of journals from Quantum Magazine. So that's covering biology, computer science, math, and physics.
Right, all the heavy hitters.
All of them. Plus a truly wild medical report straight out of MIT News. And our mission for this deep dive really is to explore this boundary that is just rapidly evaporating. We're looking at how technology and machinery are becoming, well, bizarrely organic, while at the exact same time, scientists are discovering the fundamental machine-like math and physics that govern our own fleshy bodies.
Which is exactly why we're looking at all these sources together today. Because in an age of constant information overload, which, we all feel.
Oh, absolutely.
I always argue that the most valuable skill you can develop isn't just memorizing facts. It's spotting the patterns that connect seemingly completely unrelated fields.
Right, because when you put them side by side.
Exactly. When you put a breakthrough in quantum physics next to a breakthrough in liver transplants, a much bigger, much more fascinating picture of reality just emerges.
Okay, let's unpack this. Let's start with that paralyzed patient, because this is the most literal intersection of human and machine we have, right?
Yeah.
Hacking the physical body.
Yeah, the direct interface.
Right. So according to ACM Tech News, the BrainGate Consortium has developed a brain-computer interface, or BCI, that lets paralyzed people type at 22 words per minute, which, that's basically standard smartphone texting speed for anyone.
It is a massive leap in accessibility, just huge. But the real brilliance here lies in the mechanism itself, because they aren't tracking eye movements or muscle twitches or anything external like that.
Okay.
They're using implanted electrodes to capture the raw electrical neural activity directly from the brain's motor cortex.
Wait, so the brain hasn't changed at all? Like the person just thinking about moving their fingers, and the machine somehow knows what they mean?
Precisely, yeah. The motor cortex is still firing as if the person's physical fingers are moving across a virtual QWERTY keyboard.
That's crazy.
The brain is doing the exact same biological math it always has. But here is where it gets interesting. An AI steps in to act as a translator.
Oh, so the AI is the bridge.
Exactly. We've essentially built a machine that finally speaks the brain's native language. It's predicting the intended movements just from the static of raw neurons firing.
That is incredible. But an ACM did mention a pretty significant catch here.
Yeah. Unfortunately, there is a major current limitation. The system requires recalibration every single time before it can be used.
Oh, wow. Every time.
Every single time. You have to remember, the brain is, it's biological squish. It's sitting in fluid. So the physical environment, the precise location of those electrodes relative to the neurons, it shifts slightly from day to day.
Oh, I see.
So the AI has to constantly relearn how to listen to that specific brain's accent, so to speak, every time you turn the system on.
Which brings up a really interesting thought. If we can wire up a machine to seamlessly read the biological brain, can we use engineering to rebuild the biological body itself?
Right, the other side of the coin.
Exactly. And that brings us to the MIT News piece. Sangeeta Bhatia and Vardhman Kumar have essentially figured out how to inject new organs into the body. They're calling them satellite livers.
And this addresses a dire, immediate medical crisis. Right now, there are more than 10,000 Americans on the wait list for a liver transplant.
10,000.
Yeah. And many of them are simply not healthy enough to survive the massive trauma of a full transplant surgery. It's a huge operation.
Right. It's incredibly taxing on the body.
So Bhatia's lab thought, instead of surgically implanting a whole organ, what if we could just give the body a kind of booster function by injecting liver cells?
Okay, I have to admit some confusion here.
Yeah.
Because you can't just inject a puddle of liver cells, hepatocytes, right?
What's hepatocytes?
You can't just inject them into someone's abdomen and hope they organize themselves into a liver. Wouldn't they just, dissolve or get flushed out by the bloodstream?
You are exactly right. They absolutely would. Cells need scaffolding. They need a physical, structural niche to survive and function in. And this is where the brilliant material science comes in. The MIT team used a microfluidic device to create these tiny, highly uniform hydrogel microspheres.
Hydrogel microspheres, got it.
Yeah, and they mix these gel spheres with the hepatocytes, and they also add fibroblasts, which are specialized support cells.
Okay, let me see if I've got this. It's like injecting a bunch of specialized Lego bricks mixed with microscopic packing peanuts into the body. While they're in the syringe, they flow like a liquid, but once inside, they automatically snap together to build a functioning mini-organ.
That is a perfect way to visualize the mechanics of it. It's relying on the physics of shear thinning fluids.
Shear thinning fluids.
Yeah, so when pressure is applied, like pushing the plunger of a syringe, the mixture behaves as a liquid. But the moment that pressure is gone and they are resting inside the tissue, the hydrogel spheres lock together.
Oh, wow.
They instantly regain their solid, porous structure.
And they inject this specifically into the belly fat, the peritoneal adipose tissue,
Oh, there.
of all places.
Because belly fat has a tremendous blood supply and it's highly pliable, it can accommodate the growth.
That makes sense.
Once those Lego bricks, as you called them, lock together, those support cells, the fibroblasts, act like mortar. They actively promote the growth of the host's blood vessels deep into this new artificial tissue.
So it connects to your own blood supply.
Exactly. In their mouse trials, these satellite livers functioned flawlessly for 8 weeks. They grew their own blood vessels, pulled nutrients from the host, and secreted necessary liver proteins right back into the host's circulation.
That is just a gorgeously engineered biological patch.
It really is.
So we're engineering the body with hydrogels and predictive algorithms. But why are we suddenly able to do this? So if we look at our quantum magazine journals, the answer seems to be that mathematicians and physicists are finally cracking the underlying code of biology.
We're moving from treating the body to reverse engineering its fundamental rules.
Exactly. For centuries, human tissue was considered, too messy, too chaotic for elegant math. But quantum math reports that mathematicians have finally delivered a long-sought proof that tames unruly partial differential equations, the ones that describe oxygen levels in human tissues.
And that's a huge breakthrough.
Let's pause there, though, because I want to make sure you, the listener, understand why this is such a big deal. What makes a partial differential equation so unruly in the first place?
Well, think about what you are actually trying to measure. You aren't just measuring how much oxygen is in a static cup of water.
Right.
You're measuring blood pulsing, oxygen diffusing through different densities of cell walls, and those cells consuming that oxygen at varying rates, all at the exact same time.
Those constantly changing in multiple directions.
Exactly. A partial differential equation maps out how multiple changing variables interact with each other across time and space. Taming these equations means we can now model this chaotic biological behavior with the exact same mathematical precision we use to calculate, say, the load-bearing stress on a steel bridge.
That's amazing. When you look at the biology itself, the cells are already doing their own math.
Oh, absolutely.
According to quantum biology, our cells are essentially acting like complex computer networks.
Yeah.
The old textbook model was that cells just reacted blindly to local chemical signals. But it turns out tissues use bioelectricity to make group decisions.
They do. They literally use electrical currents to coordinate and vote to expel unhealthy cells from the tissue.
They vote them out. It completely reframes how we view immunity and healing, doesn't it?
It does. It shows it as an active electrical network. The cells are constantly altering the voltage across their membranes to communicate with their neighbors.
Wow.
And we see this same overturning of assumptions happening in the brain. For decades, neuroscientists mapped the brain through connectomes, which essentially treated the brain like a vast, static wiring diagram made entirely of neurons.
All right. And in that old model, cells called astrocytes were totally dismissed. They were viewed as the janitors, just there to feed the neurons and sweep up the chemical waste.
Yeah, totally sidelined.
But the new research shows that astrocytes are actually in charge.
They really are. The old metaphor was always that understanding the brain by only looking at neurons is like trying to understand a symphony by only watching the conductor.
Right.
But it's actually more mechanical than that. The astrocytes act like the soundboard engineers in a recording studio.
Well, I like that.
Yeah, they're physically changing the resistance in the neural pathways. They act as volume knobs and equalizers, actively tuning the neuronal activity to modulate our mental and emotional states.
And if that biological computing isn't wild enough, quantum physics points out that this rule-breaking behavior goes all the way down to the atomic level.
Yes.
Physicists have recently managed to make electrons flow like water, like an actual fluid.
This is a massive paradigm shift in quantum systems. Normally, we picture electricity flowing through a copper wire like a chaotic game of pinball.
Bouncing everywhere.
Right. The electrons bounce off the atomic lattice of the wire, scattering randomly, and that bouncing is what creates electrical resistance and heat.
But now, they've induced electrons to act hydrodynamically. What does that actually mean for the physical world? Like, practically?
Well, it means that under very specific conditions, the electrons stop bouncing off the walls of the wire and start interacting primarily with each other.
Okay.
They bond together so strongly that they move as a single viscous fluid. So they smoothly flow around obstacles without that chaotic scattering. It radically changes how we manage heat and resistance in next-generation electronics.
Here's where it gets really interesting. Let's look at the whole board here.
Let's do it.
If we can write partial differential equations to predict tissue oxygen, and our cells are using bioelectric voltage to vote on tissue health, like a network protocol, and the electrons powering our machines are flowing like plumbing, at what point do we stop calling it biology and start calling it biological computing? Are humans just incredibly advanced, fleshy hardware?
That is the exact question philosophers and computer scientists are grappling with right now.
It's a little terrifying.
It is, because as human biology starts to look more and more like computing, our silicon computing, specifically AI and robotics, is moving in the exact opposite direction.
Right.
It's becoming increasingly organic and bleeding into the physical world.
So let's talk about the AI side of things. Quantum computer science highlights a massive philosophical shift happening in artificial intelligence right now.
A really big one, yeah.
Researchers are noticing that totally distinct AI models are appearing to converge on a singular, Platonic way to encode reality.
Yes, referring to Plato's concept of perfect abstract forms, the idea that the physical things we see are just shadows of true underlying concepts.
But explain this to me mechanically.
Yeah.
How does an AI model trained exclusively on text and an AI model trained exclusively on images converge on the same thing? They're looking at completely different data.
It happens inside what we call the latent space. You can think of latent space as an incredibly vast, multidimensional map inside the AI's brain where it organizes concepts based on mathematical weights.
Okay, I'm following.
What researchers are finding is that the AI trained on millions of photos of dogs and the AI trained on reading millions of sentences about dogs are eventually plotting the abstract concept of dogness in the exact same mathematical coordinates within their respective latent spaces.
Wait, really? The exact same coordinates?
Yes. Regardless of the data they are fed, they're independently discovering a universal structural geometry of reality.
And this Platonic AI reality is rapidly getting physical bodies. We're seeing this all over ACM tech news. The digital is just forcing its way into the physical. Like the U.S. Navy Pacific Fleet just awarded a 5-year contract to Gecko Robotics to deploy these wall-climbing and flying robots.
And it is crucial to understand that these robots aren't just out there cleaning ship hulls or inspecting dark ballast tanks. They are sensory organs.
Sensory organs for the AI.
Exactly. They are collecting massive amounts of physical data to feed back into an overarching AI platform called Cantilever, which uses that data to predict maintenance needs across 18 massive naval vessels.
It's happening in the civilian sector, too. Agility Robotics has a humanoid robot named Digit currently working in a Schaeffler auto parts factory in a small town in South Carolina.
I saw that.
Yeah, Digit is literally walking around carrying 25-pound baskets of bearing components to a conveyor belt.
Although there is a fascinating caveat here that perfectly bridges the robotics news with our Quanta CS sources.
Oh.
If Digit is so advanced, why is it currently mandated to work inside a plexiglass cage on that factory floor?
Because of the small stuff.
Exactly. Quanta points out that humanoid robots still lack the subtle, instinctual, physical qualia that biological humans have. They don't have those micro-corrections and spatial instincts yet.
They're too rigid.
Right. A Digit cannot reliably detect and safely yield to unpredictable human workers in close proximity. So for safety, the physical machine has to be caged while its AI brain continues to learn.
But they are learning fast. And the craziest part is how these machines are mapping the physical world. They're using us.
Yeah.
ACM reported a story about Coco Robotics, which makes those little short-distance food delivery robots. They just partnered with Niantic Spatial. Niantic is the firm behind the mobile game Pokemon Go.
It's a brilliant, if slightly unsettling, crowdsourcing feat. For years, millions of players of Pokemon Go have been taking photos of their local parks and streets to get in-game rewards.
Just playing a game.
Just playing. And Niantic amassed a staggering 30 billion images. They used that visual data to build a highly accurate visual positioning system, or VPS.
So what does this all mean for you, the listener? It means playing Pokemon Go is like being an unwitting surveyor. You thought you were just walking around catching digital monsters for fun on a Tuesday afternoon, but you were actually paving the sensory roads for an incoming robotic civilization.
That's exactly what happened.
We literally fed the machine our world, photo by photo, so that Coco's delivery robots can navigate city streets, even when GPS goes down.
We absolutely did. And this massive convergence AI model is independently mapping the geometry of reality, robots roaming naval ships and factories, biological systems being reverse engineered into math. All of this requires a staggering amount of physical infrastructure.
Oh yeah, the physical footprint.
And it introduces terrifying new security vulnerabilities. The real world has to physically house, pay for, and protect this new reality.
The cost alone is mind-bending. According to ACM, data center construction spending has officially overtaken office building construction in the U.S. for the first time in history.
First time ever.
Yeah, in December 2025 alone, we spent $3.57 billion on data centers, surpassing the $3.49 billion spent on general office projects. We are literally building more houses for computers than for human beings to work in.
And the power demands of those computers are astronomical. The cost of electrical systems for these data centers has skyrocketed from $8 million per megawatt in 2020 to $11 million per megawatt today.
Wow.
The physical footprint required to maintain this digital reality is immense.
And with all that centralized data and power comes the threat. ACM featured a major report from Akamai, which is one of the world's largest content delivery networks. They detailed a severe spike in cybercrime, and specifically tracking a 245% surge since the beginning of the Iran war.
And to look at the Akamai data strictly by the numbers, without any editorializing here, they report a 70% increase in botnet-driven discovery traffic, a 65% jump in automated reconnaissance, and a 52% surge in scanning exposed infrastructure.
Just massive numbers. And 40% of this malicious traffic is specifically targeting banks and financial technology companies.
Right.
As for where this traffic is originating, just reporting the data, the Akamai sensors detected the source IPs were primarily from Russia at 35%, China at 28%, and Iran at 14%.
The scale of this threat is so large that we are seeing unprecedented corporate alliances. Nearly a dozen major tech and retail companies just signed an industry accord against online scams and fraud.
They're teaming up.
They are pledging to pool their threat intelligence and roll out dedicated AI defenses specifically designed for rapid fraud detection.
But AI patches and corporate accords are just putting out fires, right? The ultimate security solutions of this future are relying on the absolute weirdest parts of quantum physics.
Oh, without a doubt.
Let's look at the 2025 Turing Award, which is essentially the Nobel Prize of Computing. Both ACM and Quanta covered this. It went to Charles H. Bennett and Gilles Broussard for inventing quantum cryptography.
This is a beautiful example of fundamental physics solving a deeply complex engineering problem. Back in 1983, Bennett and Broussard theorized what they called a quantum subway token.
Okay, wait. How does a quantum subway token work? How is it different from, say, a digital barcode?
It relies on the observer effect in quantum mechanics. In the classical digital world, you can copy data infinitely without changing the original file.
Right, copy and paste.
Exactly. But in the quantum world, the physical act of observing or measuring a particle inherently changes that particle's state. So Bennett and Broussard realized that if you encode information into quantum states, the token could never, ever be forged.
Because looking at it ruins it.
Exactly. Even if a thief managed to steal the entire physical turnstile used to read the tokens, they couldn't copy the token itself because the mere attempt to read the quantum key destroys it.
That's brilliant. And they actually proved it physically 5 years later with the BB-84 experiment using real photons to create unbreakable encryption keys.
They did.
But if you think quantum tokens are weird, ACM also reported on some bizarre tech out of UNSW Sydney. Researchers are using something called negative light to send secret messages.
Yes, using thermoradiative diodes. They're transmitting data at 100 kilobits per second, disguised entirely within the ambient background thermal radiation of the room.
Let me get this straight. Is that like trying to whisper a secret to someone by creating specifically timed pockets of silence in a really loud, crowded room?
That is a remarkably accurate analogy. Yeah, think about the thermodynamics. Everything with a temperature emits infrared radiation, right? Background heat.
Sure.
Instead of turning on a flashlight to send a Morse code signal in the dark, which is obvious to anyone looking, they're utilizing negative luminescence. They are intentionally dimming the infrared radiation they emit in specific timed patterns.
Oh,
So to anyone observing, it just looks like natural background thermal noise. But a specialized receiver can read those darker than usual pockets as data. It's literally security through thermodynamics.
Wow. Okay, we have covered so much ground today. From the fluid dynamics of electrons in quantum computing to injecting shear thinning liquid livers that snap together in your belly fat.
We really did. We started with minds typing on screens at texting speed, explored how cells use electrical voltages to vote out the sick, and ended up discussing robots navigating using Pokemon Go photos.
And secret messages hidden in negative light. It really hammers home why this matters to you, the learner. Think about your life right now. Whether you're catching a Pokemon on your phone, working in an office building, which, again, are now officially being outpaced by data center construction, or waiting for a medical breakthrough for a loved one. The fundamental blueprints of reality are converging all around you. Biology, math, machinery, they aren't separate categories anymore.
No, they're not.
They're all speaking the exact same language.
The boundaries have truly evaporated.
But before we go, I want to leave you with one final, incredibly provocative thought. I pulled this from the very bottom of the quantum math sources. We talked about how AI is converging on this perfect Platonic view of reality inside its latent space, right?
Right.
Well, back in 1874, the mathematician Georg Cantor published a groundbreaking paper proving that there are actually different sizes of infinity. It fundamentally changed mathematics forever.
It did.
But newly unearthed letters reveal that Cantor actually plagiarized that discovery. The human who gave us the ultimate mathematics of the infinite stole it.
Wow. It adds a deeply human, deeply flawed element to a supposedly perfect mathematical truth.
Exactly. So here is the thought to mull over. If one of the greatest human proofs of the infinite was actually stolen, it makes you wonder about the AI of today. As all these massive AI models converge on their Platonic view of reality, will the next profound discovery about the universe be genuinely discovered by a machine? Or will it just be aggregated and stolen from the billions of data points we unwittingly provided them?
That's a great question.
When we look closely at the machine, we're just going to see ourselves looking back.
A murky boundary indeed.
Thanks for taking the deep dive with us. We'll see you next time.